All right, so we are going to review what the second derivative means on the graph of a function. And it turns out that what it affects is something called a concavity. So that is going to be the focus today. I'm going to go through our worksheet on the second derivative. I know potentially one of my classes I left you partway through going through this last day, so you can skip to where we left off if you like. Okay, so first we defined what the second derivative actually means, and that's quite simple. The second derivative is just the derivative of a derivative. So, for instance, let's consider the function f of x is x to the fourth minus 3x squared plus 1. We know very well using the power rule, its first derivative is 4x cubed minus 6x. And second derivative is simply the derivative of this function. And one way to write second derivative, or derivative of the derivative, is to put two primes, f double prime of x. And that ends up being 12x squared minus 6. All right, so what? Who cares? Well, let's find out. And before I go further, just take a quick note that there's a few different ways to write the second derivative of a function y equals f of x. So if y equals f of x, we can write the second derivative as y double prime, f double prime, or this is the derivative notation, the derivative of dy dx. It's written d squared y dx squared. A little bit funky. You can use whichever one you like, but just be aware that on a test or exam, you are expected to recognize any of these three notations as meaning second derivative. So the real reason we're studying the second derivative is to ask, what does it tell us about the graph of a function? So let's go case by case here. What does it mean if the second derivative is positive at a point x, or in an interval? Well, that means the derivative of the derivative is positive, so the slopes of the tangents are increasing. What would that look like? Well, consider a function like this. What are the tangent line slopes like? Well, they start off low, getting steeper until we get really steep. So this means the slopes of the tangents are increasing. Maybe they even start negative, where they start off negative slopes, increase towards zero slope, and then go into the positive territory. So those are the possibilities, and what we call this if f double prime is greater than 0, the slopes of tangent lines are increasing, like I said, and we refer to this as opening up, or we can also say concave up. Both of those mean the slopes of the tangent lines are increasing and our graph opens up. Consider y equals x squared. Its second derivative is 2. That means it's positive everywhere, regardless of what x is, and as we know, y equals x squared does open up everywhere. Now, if f double prime is less than 0, we get pretty much what you would expect based on, instead of the tangent lines increasing, the slope of the tangent lines is actually decreasing. So maybe it looks something like this, where we start off really positive slopes, and then we gradually flatten out, it decreases. Or maybe it actually starts off positive, decreases all the way to 0, and then goes negative. So in this case, these slopes of our tangent lines are decreasing, and we call this opening down, or we say the graph is concave down. So concavity is a property of a graph, and concavity means, is the graph opening up or down? And we think about, maybe we could have a function that starts opening up and at some point switches to opening down, or vice versa. And in fact, that can happen. The second derivative can change sign from positive to negative. In order to do that, it has to go for a continuous function. it has to go, or differentiable function, it has to go through a point where f double prime equals 0. Just like to switch from increasing to decreasing, you have to go through a minimum or a maximum point. To go from concave up to down or vice versa, you have to go through a point where f double prime is 0. A point where it switches from opening up to down or from opening down to up are called points of inflection. And at a point of inflection, we have the condition that f double prime equals 0. Unfortunately, that's not enough. Just because f double prime equals 0 does not mean you necessarily have a point of inflection. You have to test to see at a point of inflection, does the concavity switch from up to down? Let's look at perhaps the most famous example. Y equals x cubed. Its second derivative is 6x. And in order for the concavity to change from opening up to down, or vice versa, y double prime has to at some point be 0, which means x must be 0. And now, to check, we actually have to use a sign diagram, which we're very familiar with, for the second derivative. So at 0, if we plug in a number like, what's f double prime of something left of 0, like -1? We get -6, which is negative. F double prime of 1 to the right of 0 is +6. So we actually see it switches from negative concavity to open, to positive concavity, opening down to opening up. And the graph, we know we're familiar with the graph. It looks like this. And we see that actually, yes, it is opening down here as part of a frowny face. And then it's opening up here. It's like part of a happy face. So it switches from opening down to up. Now, we also know the intervals of concavity. It is concave up when x is positive, and it's concave down when x is negative. Okay? So let's do another example here. Let's identify any points of inflection of f of x equals x to the 4 minus 6x squared plus x plus 10. Well, that would mean that f prime of x is 4x cubed minus 12x plus 8, and f double prime of x is 12x squared minus 12, and if we set that equal to 0, we get x squared minus 1, which is 12 times x minus 1 times x plus 1. So possible points of inflection, possible points where the concavity changes, is when x equals 1 or -1 are possible inflection points. Now let's do a sign diagram. Got -1, we've got 1. If into, let's see, like f double prime of 0 is -12, so this is definitely negative. F double prime, let's do 2, is let's see, 12 times 1 times 3, so it's positive. Is greater than 0. And f double prime of -2 is, let's see, negative times a negative, which is a positive. Okay, so indeed, -1, 1, or sorry, -1. And what do we get when we plug -1 into the original? 1 minus 6 is -5, minus 8 is -13, plus 10 is -3. And what do we get when we plug 1 into the original? We get 1 minus 6 is -5, plus 8 is 3, plus 10 is 13. They are inflection points. Okay. Now, think of the graph of 1 over x. Let's do another example here. We know the graph of 1 over x. We can see it changes from concave down, left of x equals 0, to concave up, right of x equals 0. And let's look at the second derivative. Okay, this is, remember, this is like x to the negative 1. So this is negative x to the negative 2. F double prime of x is 2x to the negative 3, which is 2 over x cubed. So 2 over x cubed is actually never equal to 0. So this graph, or this function, has no points of inflection. However, we see it does actually change. And the moral of the story is you must include vertical asymptotes, discontinuities, on your second derivative sign diagram. So if we had 0, we know we plugged in a number to the left, we would actually get negative, and a number to the right, we get positive. So even though it's not a point of inflection, it does change concavity across an asymptote. All right, so the second derivative test. Last thing. We've seen how to find points of inflection. We know how to find maxes and mins. You set the first derivative equal to 0. You check to see, does the slope of the function change at those points where the first derivative is 0, which we call critical points. But consider the case. Think about if you had a function that you knew in some region was concave up, and you knew there's a critical point there. Well, then that must be a minimum. It has to lie at the bottom of the smiley face. Similarly, if you had a graph that was concave down and you knew you had a critical point in that area, it has to be a maximum. So if you have a critical point, if you plug it into the second derivative, if it's a minimum, or if your second derivative is positive, that critical point must be a minimum. If your second derivative is negative, it must be a maximum. And I've outlined those possibilities here. Note that if your second derivative returns 0, it won't tell you anything about the point. All right, so let's do one last example. We have a function, 3x to the 5 minus 5x cubed plus 3. I tell you it has two critical points when x is negative 1 and 1. So let's use the second derivative test to see if these are local max, local min, or neither. So this test, take the second derivative. Let's do the first is 15x to the 4 minus 15x squared, and second is 60x cubed minus 30x, which I could factor as 30x times 2x squared minus 1. And let's plug those 2 points. Let's plug negative 1 and 1 into the second derivative. So f double prime of 1, 30 times 1 times 1, which is positive. So when x equals 1, we have a minimum. It's at the bottom of the smiley face. The second derivative is positive there. F double prime negative 1 is 30 times negative 1 times 1, which is less than 0. So when x equals negative 1, we have a max. And you could plug in x as 1 and negative 1 into f to get the y values of those maxes and mins. But if the second derivative is really easy to take, this test is easier than using a sign diagram for the first derivative. It's up to you usually. Sometimes you will get f double prime is 0, in which case your gamble fails and you actually have to go use the first derivative test anyway. But if the second derivative is easy, this is a great way to check for maxes and mins. Okay, so homework, pages 118, 121 to 122. All right, so try those and we'll take it up next day.